So there is a very simple technique for determining the chemical formulas of compounds with carbon, hydrogen, and oxygen. And you can also do other compounds containing other elements, but this is kind of the most common one that we talk about. But in the method, what they do is fairly simple. They take a furnace, that's shown here, and you stick the compound in it, and then they basically burn it in the presence of an excess of oxygen. Now, the products of combustion are always carbon dioxide and water for these kinds of compounds, provided that there's enough oxygen. So what we do is we take a U-tube. That's actually what this is called. Not like YouTube, but it's the U letter, right? We take a U-tube and we pass the gas into the U-tube, and they have a desiccant in there, something to pull the water out of the gas from the combustion process out of the gases. So it's actually going to absorb the H2O. So the next thing that happens is that gas travels through a carbon dioxide absorber. Okay. And then if there's anything else that's not absorbed, that just goes out. And principally what that is just unused oxygen. Now, what they do is they weigh the absorber before and after, right? And then for the H2O absorber, the mass it gains, and I'll show you what those masses look like, but the mass it gains is the mass of water. And then the CO2 absorber, it absorbs the CO2, so that's the difference is actually the mass of CO2. We can use that information to figure out what the empirical formula is, and if we have data, for example, from like a mass spectrometer, we can also figure out the molecular formula. The way this works in principle is that you take an unknown, like this compound here, and you burn it in oxygen, and it produces carbon dioxide, water, and then unused oxygen. Okay, so notice what happens. The carbon dioxide, the carbons are the black atoms, right? There are two in this formula over here. Every single one of those carbons on complete combustion shows up in a carbon dioxide. So we could actually determine the mass of carbon from the mass of the carbon dioxide trap, is what we call it. It's a trap. Now, if we look here, right, in this combustion, I have 1, 2, 3, 4, 5, 6 hydrogens. All of those hydrogens will show up in water molecules. So we trap the water molecules, we trap the carbon dioxide molecules, we use conversions to calculate masses of carbons and masses of hydrogens, and then this is the tricky part, okay? There's an oxygen in here, but there's two sources of oxygen. So what we're going to do is we're going to rely on the conservation of mass. So let's say this is our sample down here. The mass of the sample is going to be equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen, assuming those are the only things that are there. And what you're going to do is you're going to calculate the carbon from there. I meant to go to the carbon, not the oxygen. You're going to calculate the mass of the hydrogen here. And if you're given the sample mass, all you have to do is subtract, and you'll get the mass of the oxygen. Well, now that you have the masses of carbon, hydrogen, and oxygen, you can go through the process of the empirical formula, calculate the moles, and then the mole ratios, right? Then if you know the molar mass of the compound, you'll do what you just saw in the very short previous segment. Just take the formula mass, empirical formula mass, and divide it into the molecular mass, and you'll know how many times that fits into that formula, and then you can get the molecular formula. So let's go through this calculation. There's actually a couple of ways to do this. Oh, I just want to make one other note here, just right to the left here. This is using conservation of mass. Okay, so here's the problem. And these problems are all very long in their words, but we just need to pick out the key bits of information. So it says, A 0.44 gram sample of compound containing only carbon, hydrogen, and oxygen is analyzed by combustion analysis. The sample produces 0.882 grams of carbon dioxide and 0.36 grams of water. Analysis by mass spectroscopy gives us a molar mass or molecular mass of 88.0 atomic mass units. Determine the empirical and molecular formulas. Now, two things, right? There's only really 4 bits of data in here. There's this, the mass of the sample. We'll need that later, right? We'll need the mass of carbon dioxide right away because that'll give us the mass of carbon. And we need the mass of water right away because that'll give us the mass of water, hydrogen. And we'll use that carbon and hydrogen mass with the mass of the sample to figure out how much oxygen in there, and then after that it's an empirical formula problem. Now, once we get the empirical formula, we'll use this bit of information, right? That's the molecular mass, and that will allow us to calculate like how many times the empirical formula goes into the molecular formula. So here's the data. I sort of broke it down into its sort of simplest form, right? And what we want to do is we want to figure out the mass of carbon and carbon dioxide. So I'll show you 2 different ways to do it, and we'll get the same number both ways, but I want you to recognize that there's like 2 different pathways that can be done. The way the book talks about it is to convert to moles, and the way I do it is just use that percent mass that we calculated earlier. Remember, because it's CO2, that percent mass never changes, and I always like keep it handy, like in my calculator or on the back of a notebook, just in case I need it. So this is going to be using percent. And I have a 0.882 gram sample of CO2. Okay, so I'm going to just go like this. Grams of carbon, right? That's going to be 0.882 grams. And then what I need to use is the percent of carbon and carbon dioxide to get the grams of carbon. Now, I should write this CO2 here so we don't get confused. I'm going to use 27.289 grams of carbon for every 100 grams of CO2. And that comes out to be, let's see, 0.24069, 3 sig figs. I'll stop there, 69 grams of carbon. Okay, now I said there's another way to get to the mass of carbon, and that's by using molar mass. And so I'm going to write this out for you, and so you can follow along. And your book gives lots of examples of or several examples of how to do this. So you can follow along with the book, and I'm sure you can find lots of examples online. So the way to get the grams of carbon by using the mole conversion, and this is actually a very important conversion to learn, is this. You're going to say I have 0.882 grams of carbon dioxide, and then you actually will convert it to moles. Now the molar mass of carbon dioxide is 44.01 grams for every 1 mole of CO2. And then you're going to use what's called the formula ratio. There's 1 mole of carbon for every 1 mole of CO2. And so you'll see how these units are canceling out, right? Now I have moles of carbon, and now I just need to get the mass of carbon, so you can multiply by 12.011 grams for every mole of carbon. And if you do that, you still get this same number. So you didn't need to know the mass percent ahead of time. You could have just used the ratio of molar masses really to calculate the mass of carbon and carbon dioxide. So now what we'll do is follow through, and we'll do the same thing for the hydrogen from the water. So I have so I need grams of hydrogen. Let me start with that. I have 0.360 grams of H2O. I'm going to multiply that by the mass percent of water hydrogen in water. So it's 11.19, and I'm not just remembering it, it's like right up here in the corner of the slide, right? 0%, so grams, sorry, of hydrogen for every 100 grams of H2O. And then I'll go ahead and I'll do that calculation. That comes out to 0.040284 grams of hydrogen. Now again, I'm going to show you, this is using the percent, using mass percents, right? You can also follow the mole pathway, and so I do want to show you that as well. So you can go to grams of hydrogen, and you have 0.360 grams of hydrogen, and then we're going to H2O, sorry, and we're going to convert that into moles of water. So the molar mass of water is 18.02 grams of water for every 1 mole of water. Now, how many hydrogens are there for every water molecule, right? There's 2 moles of hydrogen for every 1 mole of H2O. And I just get that by looking at the chemical formula. That's why it's called the formula ratio. And then I have to convert that to grams of hydrogen. So now it's 1.008 grams of hydrogen for every 1 mole of hydrogen. And again, it's a lot longer calculation, but again, it's just calculating the mass of hydrogen that's in water. And this gives you the same result as that. So either pathway, this is the mole path, right? I should add the E, the mole path, and the other one's the percent path. Technically, I don't really care which way you do it, but you will eventually need to know like how to do both types of calculations, because the mole calculation continues on throughout the entire semester. Now, we have to do the last bit, right? Over here, we got the grams of carbon, and then we got the grams of hydrogen, right? So conservation of mass says if I add that to the mass of oxygen, that'll be the total mass, right? So our sample originally, right, weighed, had a mass of 0.44 grams. So in a sense, the mass, right, total, which is the 0.44 grams, was going to be equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. So what I need to do is solve this equation for the mass of oxygen. So that will leave me with mass of oxygen is just the 0.440, I believe it was actually, grams, minus the mass of the carbon minus the mass of the hydrogen. So this is my mass of hydrogen, and this is my mass of carbon, right? So I'll write that out. Mass of carbon was, let's see, do I have it written down? Oh, I guess I have it written on the wrong slide, actually. I have little notes on the slide, so I'm just reading that real quick. Oh yeah, I'll just do it. Let me get the numbers. I'll just write them down. Okay, so those are the numbers, and then when you do the calculation, you get 0.15902 grams of oxygen. Okay, so the last bit, all right, this is the last bit we needed to get to the empirical formula. Now we have the carbon, hydrogen, and oxygen masses. We can set up the empirical formula, so I'll write those values in. So those are the values. I just pulled them off the previous slides. I didn't figure you want to see me going back and forth through the slides. Now what you should do is calculate the moles of each element, and then we'll do the ratios, and then we can talk about how to use that with the molar mass again. So go ahead and do the moles and the ratio, and let's come back after that, and then let's see what we predict the empirical formula to be. Okay, so those are the ratios worked out. I got the moles just divided by molar mass. Notice how small the numbers are, right? This is kind of how it is with combustion analysis. And a lot of analysis in general, we don't work with large quantities anymore. So it's okay that you get these tiny numbers. Sometimes people are uncomfortable with that. So now what we do is we take the ratios and be very careful when you get these tiny numbers. The first instinct for a lot of students is just like to round to the thousandths place or round to the 10,000ths place. Really kind of try to keep track. We've had 3 sig figs this whole way. Right? Always try to make sure you have one more digit past your last significant figure. Even if that's a rounded digit, that's okay. So now, I have ratios of carbon to oxygen, because oxygen is very clearly the smallest value, right? Smallest number of moles here. So I have 2, basically 4, and 1. So that means my formula is C2H4 and O, like that. So let's very quickly calculate what that comes out to be, right? The molar mass for that is going to be 2, I'll do it down below. 2 times 12.011 plus 4 times 1.008 plus 16, because there's only 1, right? And we'll calculate that number. Oh, I can't write it there. I'm too close to the bottom of the slide. I'll do it here. And this is all in atomic mass units or molar mass grams per mole, either way. That comes out to be 44.05 atomic mass units or grams per mole. So now compare that to this, right? The end value for this formula comes out to be 88.0 divided by 44.05. This is in atomic mass units or grams per mole. It's the same number. That comes out to be 2. So that means I take C2H4O and multiply the whole thing by 2. And that'll give me C4H8O2. Okay? So that's your molecular formula. Now, again, right, the combustion analysis process is much longer than a simple empirical formula. It's like 2 problems stacked one right after the other. I would say, generally speaking, you've kind of gone the right way when the ratios come out to be fairly good, right? If you get really weird ratios for all of the elements, you probably did something wrong and you need to back up and then look at what you did in your mole conversions, look how you did your mass percents, for example.